Thank you. Thanks, everybody. Is this cool or what? My inner geek right now is on fire. This is just amazing, this whole thing. I appreciate the college inviting me out to speak about something that I just love, and I've loved since I was a small child. Aviation and everything that flies has just drawn me in for as long as I can remember. So we're going to talk about that today, about the physics of flight and what makes an airplane fly, how it flies. And just from a little bit of a history perspective, you know, humans, we're set apart from animals in the sense that we have a reasoning, intelligent mind. And because of that, we want to conquer things. We see obstacles and we want to get past them, over them, around them. And it's not hard to understand then why chariots were devised and horses were harnessed. Ships were designed and sailed because the human's mind, the intelligence, is such that we want to overcome these things. So it's not hard to understand and think about the fact that when man saw birds flying, they said, that's something I want to conquer. I want to fly like that. In early Greek mythology, if you recall the story of Icarus wanting to escape the island of Crete, his father built him a set of wings. And Icarus, being a little bit young and impetuous, as the story goes, flew too close to the sun. The heat melted the wax and he fell into the ocean. Didn't turn out too good for him. But the idea of flapping wings is what early man looked at. They figured that's the way we're going to conquer flight. Leonardo da Vinci did it. I forgot to change the slide here. Here's Icarus. Just got going. Leonardo da Vinci, an early pioneer, at least in the advent of trying to devise a mechanism to fly. He was just crazy about trying to figure out, how do I take the power of man's muscles and devise some type of a system to get the wings to flap. Of course, that idea was just not going to happen. It's not physically possible to do that. But what he did serve to do is keep that dream and that desire alive. 113 years ago, the Wright brothers were finally able to conquer flight, the first heavier-than-air powered flight. The Wright brothers did that. What we have today, as you see on the screen, is a picture of an airplane. We have finally figured out how to fly. How do we do it? And it's really just a question of balancing forces. We have forces on an airplane that are always exerted on that airplane while it's in flight, and there are four of them. There's lift, there's drag, there's weight, and there's thrust. And these forces, when we're flying, need to be in a state of equilibrium. So two of these forces will always oppose each other. Thrust will always be opposed by drag, and lift is always opposing weight. So the thrust and the weight I want to talk about just real quick, because that's an easy one for us to understand. Weight, we know what that is. It's gravity. It's what keeps us firmly attached to the earth. Thrust, we can understand that because we've all driven a car or been in a car. You step on the gas, you're thrusted forward. The two that we don't necessarily understand real well are lift and drag. So those are the two that I want to talk about today. So we'll start with lift. When we talk about lift, there are three things that we need to discuss. We need to discuss the Bernoulli equation, we need to discuss the law of continuity, and we need to talk about Newton's third law of motion. Those three things in combination are what allow us to produce lift and to overcome that force of weight or gravity. Bernoulli, if you know anything about aviation and about flying, you've heard this name, and you probably think he must have had something to do with designing airplanes. He actually died back in the 1700s, had nothing at all to do with airplanes. Actually died before the first balloon flight by the Montgolfier brothers. What he was doing was studying flows, water flows in streams, and he was studying the pressures. The Bernoulli equation states that static pressure plus dynamic pressure equals a constant. And so static pressure, static means at rest. The air is not moving, or in his case, the water wasn't moving. Dynamic pressure is the movement of the fluid. So if we look at this in the concept of a box, if you picture this box, a square box, it has, and there's no air moving through it, the air is static. And let's just say, as an example, that the air is exerting a force of 10, just to use a nice easy number, on all four sides of that box. If you move air through that box and you add some dynamic pressure to it, you put a plate up and you could feel and measure the pressure. Let's say that you move air through that box, you take two sides out and you move air through it, such that you have a dynamic pressure of 7. Well, then what has to happen per the Bernoulli equation is that the force that was exerted on the sides that was 10 has to decrease. It has to go to 3, because the static pressure plus the dynamic pressure always has to equal a constant. So when the air is not moving, if the static pressure is 10, it's 10. If the air begins to move at a rate of 7, the static pressure has to drop to 3. That's the Bernoulli equation. I'll tie this into what it means for lift here in just a minute. Let's look at the law of continuity. The law of continuity really is simply the law of conservation of matter applied to a fluid, moving fluid. And air, when we talk about aerodynamics, we're really talking fluid dynamics. Air, although it's compressible, until you get near the subsonics, until you get to the sonic speeds and the speed of sound, where air has some compressibility to it, when you're in the slower speeds, 100 knots, 200 knots, 300 knots, air does not compress, and it acts just like a fluid. So fluid dynamics works great from a mathematics standpoint when we talk about lift and aerodynamics. The law of continuity states that area times velocity equals a constant. Now, this is easy. You take a hose and you turn the water on, and the water is coming out of the hose at some velocity. Well, as soon as you put your thumb over, don't cover it up completely, maybe cover it up halfway, what happens to the velocity? It increases, doesn't it? It starts spewing out. So the area times velocity equals a constant. This is the concept that we see in a venturi. And a venturi is simply, let's say, a cylinder that has a reduced section in it, choked down section in it. So what you see on the screen is a venturi tube, and it has a wide end, and then it narrows down. Let's assume for a second that the area A in this case, is 3. And the velocity of the fluid is 9. Law of continuity says area times velocity equals a constant. 3 times 9 equals 27. What happens then when that area gets choked down? Let's say area 2 is 3. What happens to the velocity? Goes up. What's it go up to? Goes up to 9. It has to speed up to 9. Those two have to equal out. Let's look for a second, before we talk about how that affects lift, I want to talk about airfoil terminology so that you can stay with me through the slides here. What you see on the screen is a picture of a typical airfoil, and this is what's called an unsymmetrical airfoil. In other words, it has more of a flat bottom than a curve on the bottom. There are a couple of things here that we want to point out. The first one that's extremely important is the angle of attack. The angle of attack is the angle between the chord line, which on the diagram is that red dotted line, and it extends, and its imaginary line extends from the extreme leading edge of the airfoil to the trailing edge of the airfoil. That's the chord line. And then the angle of attack is the angle between that chord line and the relative wind. Relative wind is defined as that wind that is opposite and parallel to the flight path. So, if I'm flying along like this, the relative wind is opposite and parallel to the flight path. If I'm flying like this with the nose way up in the air, but this is my flight path, the relative wind is opposite and parallel to the flight path. It doesn't have anything to do with where the wing or the nose is. It has to do with where's the airplane moving. It's an important thing to understand. So angle of attack and chord line are important, and then as well as the fact that this is an unsymmetrical airfoil. If it were symmetrical, the shape of the wing above the chord line would be identical to the shape of the wing below the chord line. That would be a symmetrical airfoil. So let's look at how air moves around the airfoil. The oncoming free stream air, as the airplane is flying through the air, that air is going to hit that airfoil. And it's got to do something. It's got to split and go around that airfoil. Where the wind, where the oncoming air hits the airfoil is called the stagnation point. And at that point, air's got to make a decision. I'm either going to go over the top or I'm going to go underneath the bottom. The air that goes over the top, in the case of this particular airfoil that's shown, if you visualize, look at that airfoil and visualize the chord line. That chord line now is going to be from where that stagnation point is to the trailing edge. That's now our chord line. And if you look at how much area of wing is above the chord line versus what's below the chord line, you see that there's more area on top of that wing. What we've done there is we've created a venturi. That air is being choked down by more area of wing on the top. That means what's the law of continuity says? It says that as the area is decreased, the velocity must increase. So as that air hits, the speed of the air has to increase to go over the top surface. It goes faster over the top than it does under the bottom. And it's because of that curvature, we call it camber, the curvature on top of that wing. When the air speeds up, now Bernoulli's principle comes into play. The air speeds up, therefore the pressure that's on the top of that wing drops, and the wing is physically pulled up into the air because of the differential pressure on the bottom. Let me say that again. When you look at the picture here, you've got air going over the top, you've got air going under the bottom. The air going over the top has to go faster. It has to go faster because of the law of continuity. The air going underneath now is still moving, and because it's moving air, that means that we've decreased the pressure on the bottom of the wing as well, but not as much as on the top. So you have a net effect of the wing being pushed up into the air. That's the concept of lift from Bernoulli and the law of continuity. But we haven't talked about Newton yet. Newton has a little bit to say about this too, and here's how Newton plays into it. When that air goes over that top surface of that wing, it doesn't just go over and then just go straight again. There's some downward deflection to that air. It can't just end up back in the free stream direction that it was going. That downward deflection, called downwash, causes an action. What does Newton's third law of motion say? Action, reaction. Every action has an opposite and equal reaction. So you have additional lifting force because of the downward momentum, that downward momentum vector from that downwash. That's how Newton plays into this particular equation. All right, let's look at some pressure distributions and pitching moments about the wing. So here we have two types of airfoils. Airfoil 1 and 3 are symmetrical. So if you look at the chord line, you'll see that the shape of the wing on the top is identical to the shape on the wing, underneath the chord line. Airfoils 2 and 4 are unsymmetrical, or more of a flat bottom wing. Now what this is showing you, if you look at diagram 1, you see the lift vector. The lift vector pointing up is exactly the same as the lift vector, or negative lift, pointing down. And the reason for that is it's a symmetrical airfoil, and it's at a 0-degree angle of attack. So as we're flying through the air, you've got just as much speed over the top as you have under the bottom. Therefore, you have the exact same forces acting in opposite directions. So essentially, this wing is not creating lift. This wing would be descending because of the weight of the airplane would cause it to descend. If you look down at number 3, that's that same symmetrical airfoil, but now the pilot now has pitched the nose up so that airfoil is in a little bit of an angle, a positive angle of attack. So what has happened is that stagnation point that was hitting right in the leading edge, now when you pitch the nose up, that stagnation point hits underneath. Because of that, my chord line is now here, back to the trailing edge, and we have more cross-sectional area above. Therefore, you have more curvature, more camber. The air has to speed up even more, which causes a pressure differential, and you have lift, positive lift, on a cambered airfoil. This is how you can fly upside down or right side up. You can actually do that with a symmetrical or unsymmetrical, but you have to change the angle of attack so that you get more area above on the top side of that wing to create positive lift. Look at diagram number 2 and number 4. What you see here is an uncambered a non-symmetrical airfoil in number 2. And in this particular scenario, this wing is flying at an angle of attack that does the same thing as diagram number 1. Even though it's flat bottom chord, it's flying at a negative enough angle of attack that you've got just as much lift in the negative direction as you do in the positive direction. The other interesting thing to look here at the symmetrical versus the unsymmetrical airfoil is the aerodynamic center, denoted by CA here. The aerodynamic center on a symmetrical airfoil is the same for the positive and the negative lift vectors. If you look at an unsymmetrical airfoil, you see that the aerodynamic centers are different. So you have a pitching moment in that unsymmetrical airfoil. If that wing is out there flying by itself, it wants to tumble. You have positive lift out here, negative lift over here, and it wants to get a rolling moment, a nose down pitching moment in that unsymmetrical airfoil. Look at diagram 4, and here we have positive lift because of the angle of attack. We're creating more positive lift. One more look at the increasing angle of attack here. In these diagrams, the red hashed area shows the positive or the negative pressure area. So in other words, positive lift that's occurring. In diagram 1, we're at an angle of attack of 0, but we're still creating positive lift even at an angle of attack of 0 because it's a cambered, a non-symmetrical cambered airfoil. So you have more cross-sectional area on the top, choking off airflow. Air's got to move faster. Faster the air moves, the less pressure on the top surface, positive lift. Diagram B shows the angle of attack increasing, and the interesting thing here also is as the angle of attack increases, the center of lift, the point at which all of that lift could be concentrated, moves forward on the airfoil. So the higher we pitch the nose up, the farther forward the center of lift moves on that airfoil. And that lift vector begins to shift forward. I'm going to show you that in a minute when we talk about some of the one of the drag forces. Diagram C, we have an angle of attack of 12 now. We can see the center of pressure moving forward and that resultant lift vector angling. Now look at diagram D. What's happened here? We've gone to an angle of attack of 18 and suddenly the lift is gone. What's happened? This is the stalled condition. So when you hear somebody say, I stalled, you know, the airplane stalled, it has nothing to do with the engine quitting. It has to do with the wing reaching an angle of attack. Remember I said the stagnation point hits here. As you increase the angle of attack and increase the angle of attack, the stagnation point moves farther down on the bottom surface. What happens at that stagnation point? Air's got to make a decision. Some goes down, some actually retreats and moves up over the top surface. You can get to a point, an angle where the air just won't make it anymore. I'm done, I quit, I can't get around. That's the stall. The air detaches from the surface of the wing is stalled, weight now takes over, we begin to descend. That's the stalled condition. Let's look at the lift equation for a second here. It's really a very simple equation. It's the coefficient of lift, which we'll talk about on the next slide, times 1/2 rho, that's the density of the air, times velocity squared, times the wing area. So if you're designing an airplane, this is a very important equation that you want. As a pilot, you don't really care about this equation too much. The plane's been designed. If you're designing an airplane, you need to understand this equation and how it fits into what you're doing. Wing area, how big is the wing? That's going to go to lift. Obviously, the bigger the wing area, the more lift you're going to create. The faster the velocity. If you look at the formula, the faster the velocity, the more lift is created. Rho, or that Greek letter there for rho, the P, air density. We can't control this as the designers of the aircraft, and we can't really control it as the pilots of the aircraft either. But it has a phenomenal effect on how an aircraft performs. If we are in thick, dense air, like on a cool day at a sea level condition, the air is very dense. Okay, we have a low density. The denser the air, the more lift is going to be created. As we climb in altitude, we get up to the higher altitudes and the air becomes very thin. The lift equation tells us that we're not going to have as much lift because the air is much thinner. Or in order to create the same amount of lift, we have to do a couple of things. We either have to increase the coefficient of lift, which we can do by increasing the angle of attack, which we'll talk about, or we have to increase the velocity, or we have to increase the wing area. Well, it's not easy to increase the wing area. It's kind of built that way. There are some things you can do, but from a general standpoint, you can't really change it too much. Coefficient of lift. Coefficient of lift is dependent on the airfoil that you're flying. So when you're designing an airplane, you're going to go to airfoil tables if you're not designing your own airfoil. You're going to go to these tables, and these tables will give you things like this coefficient of lift curve. And this tells us how much lift will this particular airfoil generate at a given angle of attack. So when we look at the graph here, you see along the bottom, the x-axis, you see angle of attack, and along the y-axis, you have the coefficient of lift. As we increase the angle of attack along that x-axis, you see that the coefficient of lift increases in a linear fashion up to a certain point. In this case, up to about, looks like 16 or 17 degrees. And when you reach 16 or 17 degrees for this particular airfoil, what happens? Lift drops off dramatically. That's the stall. That's the point where the air can no longer get around, stay attached to the top surface of the wing. So for this airfoil, if I'm designing this particular airplane, I know when I reach 17 degrees in this, with this airfoil, that wing is going to stall. Doesn't matter how fast I'm going. Doesn't matter where the nose is pointed. Doesn't matter whether I'm upside down. Well, it matters if I'm upside down because that changes it. But it doesn't matter if I'm diving, climbing, turning, banking. When that angle of attack reaches 16, 17 degrees, the wing stalls. That's important for a designer to understand. As the pilot, it's nice to know the angle of attack that we're flying at, and newer aircraft now have angle of attack indicators in them, which helps give us that information. We still don't necessarily care what the angle is, we just care that we're getting close to it, okay? Okay, that's lift. Let's talk about drag for a second. Drag is a force that we can understand one part of as it pertains to flying. We understand parasite drag. We understand it because we've all driven in cars. We've all stuck our hand out the window and we feel the pressure drag, parasite drag, pressure drag kind of means the same thing. In an airplane, in designing an airplane and thinking about flying aircraft, there's three parts to parasite drag. There is form drag, there is interference drag, and there is skin friction drag. And all three of those drags, in summation, make up parasite drag. We're familiar with all of that just driving a car. When you're designing a car, you have to think about those three types: form, interference, and skin friction drag. Automotive designers think about these things. What they don't think about is induced drag because it doesn't apply. But we'll talk about parasite drag first and then get into induced drag. So you have the three types: form, interference, and skin friction drag. The form drag really just has to do with the shape of the aircraft in this case. So what I've got on the screen here are struts. The struts are those things you see between the fuselage or the body of the airplane going up to the wing. That's a strut. So the first one there is a square strut. And you can see that as the air is trying to get around that square strut, it's having a hard time. It's got a flat face, so you have a lot of pressure drag on the front side of it. And then because of the sharp edges, you have a lot of wake turbulence coming off the back side of that strut. So you have a lot of, that's a very poor design from an aerodynamic standpoint and a drag standpoint. It's very draggy. The second one is just a cylinder, a round object. It's a little bit better. It's a lot better on the pressure side, on the front side of it, but you still have a lot of wake turbulence coming off the back of it. So not the best, not as bad as a square object from the standpoint of aerodynamics and drag. The last one, however, is a great shape. As a matter of fact, it's the perfect shape. It's the best shape from an aerodynamic standpoint that we can achieve. 3-to-1 from a ratio standpoint, cylindrical teardrop. That is the best aerodynamic shape that you can get right there. You can see that the air flows around the nose of it very nicely. Because of the taper on the back, you have little to no wake turbulence coming off the back side of it. That's the form side. Another way to think about the form side is this. If you took an airplane, take that airplane that we brought over there and stand right in front of that airplane and make a plywood cutout at the shape of that airplane and then try and push that plywood cutout through the air at 120 miles an hour. That's form drag. There's quite a bit of it. Interference drag. Take the teardrop perfect shape that we just looked at. Now I know that this old biplane isn't the perfect shape, but visualize an airplane that's that perfect teardrop shape. Perfect from an aerodynamic drag standpoint. Now put a wing on it. Well, that wing, where it junctures into the side of the fuselage, creates interference. The air trying to get around it, that wing is creating interference. Stick landing gear on it, creates interference. Put wing struts on it, where the wing hits the fuselage, where the strut hits the fuselage, where the strut hits the bottom of the wing, creates interference. That's interference drag. The last type of drag is skin friction drag. If you took the skin of the airplane and you peeled it all off like an orange and you laid it out flat on the ground and you measured the square footage of that skin area, and then you try and run a fluid, the air across it, there's friction to it. That air just trying to move past that skin, there's a frictional force dragging it back. That's skin friction drag. So all three of those, skin friction, interference, and form drag, the summation of all three of those types of drag is what we call parasite drag. And again, this is you find this in auto engineering. You find this in anything that's going to move through a fluid. You have to deal with these three types of drag. In aviation, we have another one. We have induced drag that we have to deal with. Induced drag is a byproduct of lift. As soon as a wing begins creating lift, it begins creating drag. It is induced by the creation of lift. And to visualize what that is, if you look on the screen and you look at the airfoil we have here, you see the chord line going through there. You see the relative wind, so you see that angle of attack. Remember we talked about downwash. That air going over the top surface of the wing, it's going to have a downwash off the backside. That downwash effectively changes the relative wind. You have an effective relative wind because of that downwash. Now lift. What direction does lift operate? Lift is going to operate totally opposite weight. Weight acts this way towards the center of the earth. Lift is going to act in the opposite direction. So on the diagram, what you see is lift in the gray vector acting perpendicular to the center of the earth, and in the red vector becomes an effective lift vector because we've shifted that relative wind. And look at the induced drag, that black vector. So the more the higher the angle of attack, the farther those vectors separate, the bigger the drag, the larger the component of induced drag. All right? So with aircraft, you have parasite drag, you have induced drag. Parasite drag, we all understand. The faster we go, the more drag we have. Makes sense. Induced drag's the opposite. The faster we go, the less drag we have. Because when we're flying fast in an airplane, the angle of attack is very small. Flying very fast. To fly slow, we have to pitch up, increase that angle of attack. As we do that, those lift vectors, the lift vector and the effective lift vector begin to separate. When you do that, your induced drag gets larger and larger and larger. So the faster we go, the less drag from an induced standpoint, the more drag from a parasite standpoint. So we have drag curves that here's a picture of induced drag, if you could see it. The vortex coming off of the wingtips. This is what it looks like to visualize induced drag. The drag curves on an airplane look like this. This is total drag. So on the x-axis we have airspeed, and on the y-axis we have force or drag, the force of drag in this case. The parasite drag, the green curve, you can see increases with speed. The induced drag decreases with speed. And there's a point where those two drag curves intersect, and that's a very important point from the standpoint of both aircraft design and pilots understanding that as well. And it corresponds to a specific airspeed. It's different for every airplane, different for different configurations. If you put flaps down, you change things. But in a clean configuration, by clean I mean the flaps are up, the gear is up, whereas we have as little drag as possible. In a clean configuration, as an example, that speed may correlate, let's say it correlates to 100 knots, okay? What that tells me as the pilot is that if I want to go as far as possible, I want to fly at 100 knots. And the reason for that is because if I go any faster than that, I've got more drag. If I go any slower than that, I've got more drag. I've got more parasite drag if I go faster. I've got more induced drag if I go slower. So that's an important airspeed to understand, and it's typically, we think about it in an emergency situation. It's the best glide speed. So if you pulled your engine to an idle position and you're just gliding, that's the speed with which you're going to cover the most amount of ground because you're at the least amount of drag. It also correlates to a speed, or very close to a speed we call VY, which I won't get into here today. So that's our total drag curve. Let's talk about stability and control real quick. We've talked about lift, we've talked about drag. The Wright brothers did something that no one else before them was able to do, and that is they were able to control the airplane. You had people like Octave Chanute and Otto Lilienthal, which were successfully flying gliders prior to the Wright brothers. But they didn't really have a great method of control. They hung themselves from the bottom of the glider and they used their weight. They shifted their weight around in order to control the airplane. And that was okay, and it works. But what the Wright brothers did is they developed a mechanism for warping the wings and twisting the wings. And they had rudders, and they had an elevator. They actually had a canard. They had the stabilizing surface was in the front. Nowadays you see it in the back of the airplane mainly. But when we talk about stability and control, we're talking about how do we keep the airplane stable when we're flying. The airplane operates and moves around 3 axes. All of those axes pass through the center of gravity. Everything has a center of gravity to it, the center of mass in this case. So we have a longitudinal axis which runs from the tail through the nose of the airplane. We have a lateral axis which runs from wingtip to wingtip, and we have a vertical or normal axis which operates vertically right through the center of gravity. All 3 of these axes operate through the center of gravity. The aircraft pitches, nose up and down, around the lateral or on the longitudinal axis. It rolls around the longitudinal or on the lateral, and it yaws left and right around the vertical axis. When we're talking about stability, we talk about it from a static standpoint and we talk about it from a dynamic standpoint. And now static in this case doesn't mean still or at rest, and dynamic doesn't mean moving. In this case, static means initial. What we mean is what happens initially to an airplane from a stability standpoint. Dynamic means what happens over time with the airplane when we talk about stability. Now we're going to discuss stability right now only in pitch, but understand that these concepts that I'm getting ready to talk about, they apply to pitch, roll, and yaw. They apply to all 3 axes. We just don't have time to get into all of them. Static stability, as I said, is initial tendency. So let's imagine for a second we're flying the airplane, and we are in, I haven't used this word before, we're in a trimmed condition. What a trimmed condition means is that we have adjusted the elevator, which operates when you pull back and forth on the stick or the yoke, the elevator in the back of the plane allows the nose to pitch up and down. We have a little tiny control surface on that elevator that allows us to lock the elevator, so to speak, in a position where we can take our hands off the stick and the plane will fly just fine in whatever pitch attitude we have trimmed it for. So let's assume we're trimmed or we're flying along, and we take the stick or the yoke and we push forward such that the nose pitches down and we let go of the stick. What happens immediately? What happens initially? That defines the static stability of the airplane. And the static stability of the airplane falls into 3 categories. It's either statically stable, which means it has positive static stability. It's neutrally stable, which means it's statically neutral, or it's unstable, which gives it which is negative stability from a static standpoint. So if we push the stick forward and we let go, and the nose of the airplane says, oh, wait a minute, I want to be here because that's where I was, and it immediately, initially says, let me pitch up, then we have a statically stable airplane, positive and static stability, and that's usually what we want in most cases. There are some cases where we don't want that. If we have a fighter airplane or we have an aerobatic airplane, we want some instability in the airplane, okay? But for most aircraft, we want a positively static aircraft. If we push forward on the stick and we let go and it just continues in that dive, we have a neutrally stable airplane from a static standpoint. If you push forward and let go and it keeps going, that's a bad thing. That's negative stability, and we don't want that. So that's the static stability, either positive, neutral, or negative. Generally, we want positive static stability. We want the airplane to try and initially return to where we were flying. Dynamic stability speaks to what happens to the airplane over time. So let's go back to the example we had where in the airplane we have it trimmed. It's a positively static airplane from a stability standpoint. We're going to go the other direction here. We're flying along. Now we pull back on the stick or the yoke. So the nose pitches up. We let go. What happens? Well, we know because it has positive static stability that it's going to want to pitch back down. It's going to want to return. Well, if this is the plane, the altitude we were flying on, and we pitch up, it can't just do that. It's not going to do that. It's going to fly below our flight path. It'll speed up, it'll climb up, and it'll oscillate. But it will, if it eventually over time gets back to a level flight attitude where we had it trimmed, then we say that the airplane is positive in dynamic stability. Over time it returns to its trimmed condition. Same scenario, pull back, let go. If the airplane begins to oscillate, but it just does that and does that and does that all the way to Cleveland, then we say we have a neutrally dynamic, we have a neutral dynamic stability in the aircraft. So over time, the oscillations don't get worse, they don't increase, but they don't get any better. We just fly along like that. Worst case, pull back, let the nose come up, and the oscillations get worse and worse and worse. And in that case, you can expect structural damage at some point in the near future. So that's not a good thing either. So that's the stability of the aircraft, static and dynamic stability of the airplane. And remember, that's about around all three axes, not just in pitch. An aircraft designer designs the aircraft in roll stability. So if you put the aircraft into a bank, what you'll find is that if you take your hand off the stick, the airplane will start to turn, but it'll start rolling out and it'll go wings level again because it's designed to be stable. If you step on a rudder and you kick the nose one way and you take your foot off the rudder, it wants to come back because it's designed to want to come back. If it's static and dynamically, positively a stable aircraft. Now think about controllability of the airplane. If it's a fighter aircraft, you want the airplane to be very, very maneuverable, very, very maneuverable. Therefore, you don't want a lot of stability. In fact, you want it to be unstable. You've heard the term fly-by-wire. Fly-by-wire is because the airplanes are so unstable that a human physically is unable, the human will not be able to fly it. It's just too unstable. You can't keep control of the airplane. It's so unstable that a computer has to fly it. So that's an example of where you want to design an airplane to have negative stability statically as well as dynamically. But not in these types of aircraft, and certainly not in the 737 you take to grandma's house. You want that to be a stable airplane. Center of gravity effects on stability. We talked about the center of gravity. All the axes come through the center of gravity. In the diagram here, you see a forward CG limit and an aft CG limit. The designers of the airplane will give this to us. They'll say, look, when you load the airplane, and we as pilots, we can put big heavy people in the front, or we can put big heavy people in the back, we can put a lot of luggage back there, and we can move that center of gravity to a place where it becomes a very dangerous airplane to fly. When I just talked about static stability, pitch the nose up. If the CG is too far back, you may not get out of the stall. The nose won't want to come back down. So center of gravity affects the stability of the airplane in good ways and in bad ways if we're not careful. That's all I have, guys. Thank you so much. I've really enjoyed this a lot. I'd love to talk more about this stuff. I love talking about it. I'm right over here if you want to talk about it.